The lectureship ad for the MSP lecturer is going to go live Friday, Monday, something like this. So it's currently on the redeployment register in case anyone internally would like to apply. And that's not going to happen, so it will go live on after a week. And then the deadline for applications is 1st of April, the standard jokes. And we'll have interviews towards the end of April. So I guess once it's live, we should make sure that we spread it everywhere and tell our friends, and send it to mailing lists and so on.
So when we share it with friends, what are we allowed to say? Is there anything?
What would you like to say?
People asking.
Yeah, so only good things, obviously. No, but I mean, you can say whatever you want, basically, in the sense that.
Don't request it.
So you are not sharing it officially, right? I mean, there's going to be an official ad on the university webpage, where presumably we're not allowed to say whatever we want, but that has been approved, and now you are just sharing a link to this, basically, so you can have whatever context you want. Right?
But yes, whatever you do, don't tell the truth, which is that this is a regular lectureship, not a Chancellor's Fellowship. Yeah. So we will not be boiling you like a frog, we'll be boiling you like a lobster.
So it is a regular lectureship. The word Chancellor's Fellowship does not appear anywhere in this ad.
Yes, indeed, that's what I mean.
Yeah.
There's it's straight in with lots of work.
What is the difference?
So Chancellor's Fellowship nominally starts with less teaching, and then it ramps it up over 5 years. This will probably start with teaching straight on, but there is not that many classes that are screaming for workforce, right? So I don't think anyone's going to be loaded with free classes.
Yes.
Maybe another.
Yeah,
possibly.
There's that.
So the starting date would be August, so at least there are no MSc students.
Yeah. Also, there's the fine tradition of making anyone who doesn't run away fast enough teach CS 207. So we need people who have learned to run away fast enough.
Jan asked if the interviews will clash with the away days.
Sorry?
Jan asked if the interviews will clash with the away days.
If the interviews will not clash with the away day, because we have cunningly delayed the announcement of the away day. Is there an update on the away day? Will there be one soon? Yeah.
Something Bob's organising.
Okay.
Yeah.
Any other announcements?
Craig's visiting this week.
Right. Hello,
Which
Craig.
means that I'm probably a continuum person rather than a Strathclyde person at this very moment. So.
Do you want to say hi, Craig? Okay. Any other announcements? So there's going to be MST tomorrow, is that right?
Yes, in the afternoon. And I will make some vegan cornflake clusters. So, just
Okay.
get some vegan butter.
Any other announcements? No.
Well, just remind folk of the department Jedi business this week, asking people to show solidarity with LGBT plus people by wearing a bit of purple, like that lovely chair in the corner. And whatever you do, don't say bathroom.
What is the occasion?
So this being LGBT plus History Month, the last week of the month is set aside for spontaneous demonstrations of solidarity. I believe colleagues have been invited to pizza lunch on Wednesday, and we are requested to have some sort of purple aspect to our appearance, which in my case won't make the slightest bit of difference. But you know, it would be nice if people joined in. Yeah, excuse my cynicism, but it's clear that, well, it's clear to give them some credit that the university are operating maybe if we don't say bathroom, we can carry on doing it the way we already like.
Okay. Are you chairing this excursion? Okay, so I thought, because I've done some work in a setoid model of type theory recently, I thought could be good to just give a basic introduction to setoids. To know, who knows what a setoid is? Most people, but let's take it from the beginning, just in case.
I mean, who knows what is?
So I put some references here so that people that are bored can think about what papers they could possibly be. Hopefully they're readable. So let's just start with a definition of a setoid. So a setoid consists of lots of things. So X and a tilde and an R and an S and a T is no, it's a type X together with a relation tilde from X to prop, and R is a proof that this relation is reflexive. So for every X in X, we have X tilde X. S is a proof that this relation is symmetric. I have X0 and X1 in X, and I have that X0 is related to X1, then S will tell me that X1 is related to X0, and T is a proof that this relation is transitive. So X0, X1, X2 in X. X0 is related to X1, X1 is related to X2, then X0 should be related to X2. Right. Okay, and then there's many things you could ask, but the first thing I would ask is, what is prop? So I said that this relation should take values in prop. And there's a few different answers. So you could say, well, prop is just a synonym for type. We really take propositions as type, literally. So maybe you still would like to write prop to kind of signify that this should be thought of as logic rather than data. But we could still say, okay, it's really just the type. This is what's happening in. Right, so this is the Agda standard library solution for choice. So if you look in the Agda standard library, they have a notion of a setoid, and the relation just goes into type. Right? But if you do this, then it's really quite horrible in practice, I would say, because that now means that two setoids are, when are two setoids equal, well, the type should be equal, the relation should be equal, and these proofs of reflexivity and so on should also be equal, right? That if you have slightly different proofs of symmetry, then these are not going to be considered to be the same setoid, which is kind of horrible in practice. So
So they're equal as the isomorphic.
Yes, you could, but that's not what it is, right? I mean, you could. I mean, if you go down this way, I think you'd end up making a setoid on setoids, and saying what it really means for two setoids.
Will
to be
we
equal.
also need a setoid on setoids? On setoids?
Yeah. Fun.
Could you repeat the question?
Okay. So Bob's question was, can we not say that they are equal if they are isomorphic? Which, when you restate it like that, kind of leads to the answer that yes, you could, but then you would have a setoid of setoids, where you declare this to be the equality of setoids.
Also, my question is, in which sense of equality are you talking about?
Yeah.
I mean, are you talking about some sort of proof relevant, potentially equality relation, or are you talking about when the type checker considers two setoids to be?
So the question was, what do we mean by equality? Are we thinking of some proof relevant relation, or what the type checker considers to be equal? And I mean informally what the type checker means to be equal.
Because then there's no prospect of that being up to ISO, right?
No. But you have the internal, you can have a setoid of setoids, and then you have this internal notion of equality. Okay, but horrible in practice. Okay. You could also say that by prop, we mean the notion of proposition from homotopy type theory, where something is a proposition if it has at most one inhabitant, right? So for any two inhabitants, we can prove that they are equal. Could be no inhabitants, because false should be a proposition. And I would say that this is probably morally the right choice, in the sense that you would like to be able to prove that something is a proposition. So this is the notion that allows you to do that, right? But still horrible in practice.
Do you get the same problem, or do you get different problems?
It's the same problem, but in theory, you can overcome it, right? In the sense that if you make this choice, then two setoids will be equal according to the type checker if you can prove that x is equal to x prime, and you can prove that this relation is equal to the prime version of that. And you know that because these things live in an H prop, you know that all proofs of reflexivity are going to be probably the same and so on, right? So you can, with more work, you can show that the only thing that matters are the first two components, but you still have to do that work. And you might still have to transport along these proofs of quality when you do other things, right?
A little bit better.
So it's better, but still a lot of work to do. Right?
And the relation has to be equal, it's not like extension.
Yes, if you have univalence, then it's actually enough that you have maps in both directions. But again, it's not for free, right? You have to actually explicitly invoke this fact. Okay, the third choice you could make is that you could say that prop is the type of strict propositions, which confusingly is called prop in Agda. I think it's called S-prop in Rock. So this is the type where we just have proof relevance by magic by the type checker, right? So the type checker, if you have two elements of P lives in S-prop, and you have X and Y in P, then the type checker is just going to treat these as the same thing, right? The downside of this choice, of course, is that you can't prove that something lives is an S-prop. It's kind of a syntactic criterion that only things that have been declared live in S-prop lives in S-prop. So how did I phrase this? I didn't have anything. I was saying that's
It's like definitional propositionality as opposed to propositional propositionality. Yeah.
Could the S stand for syntactic then?
I guess it could. I think it does stand for strict because things are really strictly propositional, right, on the nose. Okay, and I really thought this would be very limiting, that you can't prove this, but surprisingly, it seems to work quite well.
I think the S stands for Socratic because it interferes with the computational world only by absurdity elimination,
Yeah.
not in any more positive way. Propositions are only used to tell you not to do bad things, not to tell you what to do.
Yeah, so that's another difference between H-prop and S-prop, right? That H-prop, you can get out of an H-prop if you can prove that there's only one way to get out of it, if your way of getting out is unique, right? You can't do that for S-prop because you have this syntactic restriction. So the only thing you can do with S-prop is you can show that you can get to the S-prop version of falsity, and then that S-prop version of falsity you can get to anything you want, right? So you can get rid of impossible situations, but you don't have unique choice.
And the canonical example of something that lives in H-prop but not S-prop is termination proofs.
Yeah. Unless you implemented a broken type theory.
Please no.
Okay, so I think for most of what I'm going to say, it doesn't really matter what prop is, but if you press me, then I'm going to say that in this talk it's S-prop, right? The convenient version that you wouldn't think actually works, but it seems to. Let's look at some examples. Actually, let's do a second.
Of course, with a different audience, you had the suggestion that maybe it could be cool.
Yeah, no, that's saying that. Like,
Okay, so it could be bool, sure.
you can then have, but I mean that's similar to HPOP because you then have to always be listing it into a type, right? Or maybe.
No, I mean the problem with having it be bool rather than prop or type or whatever you want it to be is that you could only then have you force everything to have decidable equality, right?
Right.
Oh yeah.
Or you force bool not to be computable, you know, which is what everyone else does.
Maybe is there comments? No.
I thought there's another one where like this delay.
So Bob is saying that we could also choose prop to be delay of unit, which is like semi-decidable in a way. But if it's true, then you know it, and if not, you could always hope to prove it tomorrow. Right? Yeah, I don't know how that would go.
I think if you get
So nothing's really false. It's just
no, there's
maybe true tomorrow.
You can treat it as a logic a bit, but there's no. You only get geometric logic.
Right.
You don't get false. You get.
Okay, so let's just stick with S-prop for now. And I'm next going to define that a setoid morphism from one setoid to another, and like everyone else, I'm not going to bother to write out the reflexivity proofs and so on, because we can hopefully, well, we can't infer them, but we know on a whiteboard we would like to not write them. So what is a setomorphism? It's a function between the underlying types that respects equality. So if x0 is related in x to x1, then we demand that f applied to x0 should be related in y to f of x1. Because we would really like to think of this as the equality relation of the type. And of course,
You should indicate that the function is called f.
yes, thank you. Yeah, so we would like to think of this as equality, and of course, functions should respect equality, right? And why do we have setoids to start with? Well, it's exactly because we don't really have quotients in many foundations, right? So we would like to think of this as x value. This is our notion of equality. But if we are working in plain type theory, then we don't have a notion of a quotient. But many things we work with are quotiented, right? They are not just inductively generated, so just the real numbers or some kind of functions, something like this. Yes, that's a question.
Yes, so I would have expected that morphisms would be relations that are functional up to the equality, but instead it seems that they're just like actual functions.
Right, so you might, so the question was, why are the morphisms not relations that are functional up to this notion of equality? And I think as long as you're working directly in type theory, I think it doesn't matter. If you're working in a topos or something like this, then maybe that is the right answer.
Yes.
That said,
Proof of functionality in Google.
yeah. Okay, and one thing to note is that yes, so we don't want to have a separate logic. Right?
You only have the total things.
Yeah. One thing to note is that these setoid morphisms, we are not asking for them to actually preserve the reflexivity proof or the symmetry proof and so on, right? Which, if prop is H prop or S prop, then this will happen automatically because everything, all proof of reflexivity will be equal and so on, right? But even if it shows prop to be type, like they do in the Agda standard library, then the notion of setoid morphism is not required to preserve these things because morally we think of these as properties even if they are data, right? So we don't want to preserve this property of this particular reflexivity proof. But
is this part of why setoids aren't groupoids? Because groupoid, you do want to preserve, composition on your printers.
I guess so. Yeah. So the question was: is this why setoids are not groupoids? And I guess you're saying that well, you could see this as the hom, and this is saying that everything has an inverse and so on. But well, if you're in these two situations, setoids are groupoids, right?
Yeah.
Because things are equal. And just one note that if you look up the notion of an exact completion in category theory, then you'll find that it's actually more or less exactly the same as this. So I think if you just take the exact completion, then I think you're in the prop equals type case. Take the x-lex completion, then I think things are forced to be monomorphisms, and you're basically in the S-prop case.
Yeah, I think in a sense this is returning like the history behind the notion. So we start with functions and then we explain that they have to respect some kind of relation. With if you're again formed by the homotopy approach and the geometric intuition, this is taking segments to segments, right? If you're saying I have two endpoints and a path between them, it's going to output another such segments.
Right.
And then you recover everything through reflexivity if you want to get your hands on the function.
So Guillaume is saying that looking at this requirement to preserve the equality, you could, if you think of this as a path from here to here, then this is saying that the function has to preserve the endpoints of the path. And everything else is going to follow by continuity, basically. Okay, let's look at some examples. So let's take the natural numbers with relation where we say that 0 is related to 0 and the successor of n0 is related to the successor of n1 if n0 is related to n1. So generally, if you have some kind of inductive type in your meta theory, you could always turn it into a setoid by saying that equal constructors are related, right? So I want 0 to be related to 0 and successors to be related successors if all of the arguments of the constructors are related. So there's a systematic way of turning any inductive type or any inductive family into a setoid. And
Is it obvious for families because the type of further arguments may depend on the type of previous ones?
it's not completely obvious, but we have a formalization in Agda that does it.
So do the families have to be set of sorts? You have to respect the equality.
Yeah, so right. But if you have a description, then you can interpret it into the model. And then for these simple examples, you can prove that this is reflexive and transitive and so on, right? But if you live in SPOP land anyway, there's really no harm in just adding in this as a reflexive transitive closure. And it makes your life a little bit easier. Right? It also then extends to quotient inductive types eventually, where it's not true anymore that things are, for example, reflexive or transitive. Okay, let's look at another example. If I have two setoids x and y, then I can construct a product by taking the product of the underlying types and then say that x0, y0 is related to x1, y1 if x0 is related to x1 and y0 is related to y1, right? That's what you would guess, of course. And you can show that this really is the product in this category of setoids. So there is setoid morphism projections, and it has the universal property and so on, right? So you could say, okay, this is the natural thing to define the relation to be, but it's actually the only thing you can define it to be if you really want it to be a product, right? So, okay, so you could say that, well, in all of these cases, we basically do the obvious thing on the carrier, and then we define the relation afterwards. But if you look at the function type, so we have a notion of a setoid morphism. We would like to have a setoid of morphisms. And you could think, well, surely we're just going to take all of the functions from the underlying type of x to the underlying type of y. But if you do that, and then of course you have to prove that your relation is going to be reflexive and so on, then you realize that actually there's no reason why the related, okay, that's I should leave some space. So if you define a relation, then if we have some kind of functions, then what is the natural thing we could say for these to be related? Well, the natural thing we could say is that if x0 is related to x1, then f of x0 is related to g of x1, right? And y. So that's only the really compositional thing we could write here, right? We could say everything is only related to itself or something like this, but then when we try to prove the universal property, then we wouldn't have. But now, if we just take this definition and we try to prove that this is reflexive, then we have to show that f is related to itself, right? So we need to know that if x0 is related to x1, then f of x0 is related to f of x1. Right? But if f is just a function, there's no reason why f should actually preserve this equality, right? So we need to take all the f's that are extensional in this sense. Right? Okay, and then here, this proof of extensionality plays no role for when things should be equal, right? Because these proofs live in a prop anyway, so they will.
Isn't that exactly the definition?
Yes, yeah. So it also makes sense, right? That this is what you want. But what you do see is that in all of these previous cases, we could first define the carrier and then we could define the relation. Here, we have to mix the carriers and the relations of the things we're building up, right? Which makes it a bit different. Okay. And what we also see is that so we kind of just went for the obvious definition, but it's also the definition we would like, right? In the sense that it really says that functions are equal if they are pointwise equal.
I mean, you said it's the obvious definition, but I think at least to me, like the first definition I would write down, not quantifying over the past in the
To say
you
for,
say, for all x0, f(x0) is related to
Right.
achieve x0, which wouldn't have forced me to do this.
that's true. Yeah.
So
But then, okay, that's another obvious definition to not say x or x1, but just say x.
Yeah.
But then when you try to define the evaluation as a set of morphism, it would not actually be a set of morphism.
yeah.
But you're right. There are two
What
options.
would it be?
Pardon?
What would it be?
It would be a setoid. It has no universal property. Many things don't have universal properties. Oh, do you have a comment? No.
But you could have a generic thing where you define just using a normal set, and then your partial set is symmetric and transitive.
Right.
Then you can say flexible.
Yeah.
So what's going on?
Right. So for the internet, Bob is saying we could define just the thing without this condition, and it would be symmetric and transitive. So it would not be a full-on set-on, but then you can take the reflexive core of this, and that will give you the same thing. Yeah.
But also you can do a lot of this in reflexive. Partial sets.
Right. Right. You could. Right. So you could have a theory of partial setoids.
Relations switch. Because then you can't just extract a function.
Yes.
And so isn't only for functions that the definition is surprising? Or is it a positive, negative type thing?
So the question was, is it only for functions that the definition is a bit surprising? And I would say it's, maybe it's the same thing. It's for all kind of definitions that involves a function type, right? So for example, if you look at an inductive type where you have countable branching trees, so you have a root and when you have a function from the natural numbers into trees, you get a new tree. Then again, there you need to restrict to just the extensional functions, right?
It's everything which is like an internally parameterized by setoid.
Yeah.
The products and co-products are parameterized by some external notion of zero.
Right. There's two of these, yeah.
Functions parameterized by this.
Yeah, I was trying to think of a clean inductive type, because usually they have the same, a bit the same as functions, but streams are indexed just by a natural number, given the positions.
Okay, so there's some examples. See that gives the right notion of equality for functions, which is nice. And you could also see that it's very easy to take quotients informally, because we can take a setoid, we can throw away the equality it used to have and give it whatever equality we want, right? Which is like taking the quotient. But the downside, of course, is that now when we work with these things, we really want to work with setoid morphisms, for example, right? So whenever we define a function, then we have to make sure that this function respects equality. So we have this extra proof obligation.
Before with quotients, you said you can just throw away the equality, but if it's a real quotient, shouldn't it be like strictly coarser than the one that you had? Like it should preserve all equalities of the previous one.
Yes, but the quotient that you replace it with should be a predicate on the previous thing, right? So it should already respect the equality. Which leads me to this. So one thing that people call setoid hell is this proliferation of all of these proof obligations, right? That whenever you define a function, you should prove that it's nice. And whenever you get given a function, you also need to ask for a proof that it actually respects equality, right? I think this is not so bad in practice, because it's, I mean, it's kind of linear in the number of proof obligations, right? And it's just one more thing, and you could probably automate this, and I think Rock does automate a lot of this actually. The thing that's really painful, I think, is that when you have a property of setoids, so when you have P into, well, if you just go into set, is one thing, but often you really want to have a family of setoids, right? Then what should this be? Because in some sense, for every element of X, you want to have a setoid, but the elements of X should be considered equal if they are related. So we should get equal setoids whenever things are related here, right? So we need to say this. And if we just try to do some mathematics in Agda, then it's kind of annoying to ask for all of these extra structures. I think this is where the real setoid hell is, right? So one answer of what this is, there's a few equivalent definitions. So for example, we could say that family of setoids over a given setoid X is given by some kind of underlying function, which goes from the underlying, well, it's just X here, I guess, into type. And then we would like this to be a family of setoids. So we want to have an equivalence relation on each P of X, but it also should respect the equality of X. So we want to have some kind of homogeneous equality, which says that if x0 is related to x1, then we get a relation between P of x0 and P of x1 into prop, right? So if these happen to be trivially related, then we just get the relation on P of x0, but they could be equal in some other ways. And then we want this relation to be reflexive, symmetric, and transitive, but that doesn't make sense on its own because we have different indices here. So they have to be reflexive over the reflexivity proof of X and symmetric over the symmetry proof of X and so on, right? So I want to have an R which says that for all X in X, well, over R of X, that says that X is related to itself. I get that, right, so, and for all P of X, I get that P is related to P. And similarly, I want a symmetry proof, which says that if I have, how do I write it? Let's say this. I have P0 in P of X0, and I have P1 in P of X1, and I have some proof that over X01, P0 is related to P1. Then I want to get a proof over the symmetry of this. It says that P1 is related to P0, right? And the same thing for transitivity, right? So I think this is what's really painful, because whenever you want to do something with some kind of property of setoids, so it's a setoid itself, it has an interesting notion of equality, and it should respect this equality. And you really need to ask for all of this data, right, to do it properly. And that's really painful, and that's why we are in hell. So in the last 10 minutes,
so earlier you said when you have something that looks like a function, you want a separate morphism underlying the thing, but here you were going back to just the standard function from the domain. Could you not define what it means to have a setoid quotiented by, I mean, I don't know, probability like by implication or whatever, and then say that families of setoids are.
Right, so the question was, could we not turn this into a setoid and then ask for P to be a setoid morphism from here to here? And the answer is yes, we could do that. That would be equivalent.
Okay.
Or rather, we can look at this as the category of setoids, and then we can turn this setoid into a discrete category, and then we can ask for a functor from here to here. But then again, we would need to actually preserve the identity and the compositions, right, in order to get something that's equivalent to this definition. So that's another way to do it, but I think it's an equivalent definition, and I think in the amount of work, it's about the same thing. So yeah, the data you ask for is a little bit smaller, but now you have these additional proof obligations that you really preserve reflexivity and so on, which is a bit unnatural, right? Okay, so let me show you one thing you could do if you wanted to avoid this hell, which I don't think anyone's going to do in practice, but it's kind of nice anyway, right? So rather than working with this, like this, so rather than working in hell piece by piece, we can build a model of type theory using setoids. And then we can just work in this model, and the translation from this model into kind of our meta theory is going to do all of this for us. So how do we do that? Well, we're going to say that our contexts are given by or interpreted by setoids. So whenever you build a model of type theory, you always have an idea that I want my types to be setoids. That's what I'm saying when I want to set a type theory, right? But in practice, what you have to do is you have to take one step back and say that whatever you wanted your types to be, that's what your contexts are going to be. Because you could always have a context with just a type in it. So you need to be able to do this. And then your types in context gamma are going to be families of setoids over gamma, right? So this is also what always happens. You want the types to be some good notion of family over the thing you really cared about. And we notice in particular that if X here is trivial, so it's just the unit setoid with exactly one element, then all of this boils down to just a setoid again, right? Because there's only one way that the unit can be related to itself. There's only one element, so this just becomes a relation. The flexibility proof here is going to be trivial, so this is just says that P is related to P and so on, right? So we recover the closed types as the thing we wanted, setoids, but we always have to generalize and make the open types be more complicated, right? Okay, and then what do we say that our terms are going to be? So the term in context gamma of type A, well, that should basically be a setoid morphism from gamma to A, right? Except that that doesn't quite type check. It's going to be a T, which for every gamma in the underlying carrier of gamma is going to give me something in A. So this is a family over gamma. So it's one of these. To go to A gamma. Okay, so that's like a function from here to here, but I also want it to respect the equality, right? So if gamma 0, if I have gamma 0, 1, which says that gamma 0 is related to gamma 1, then I want that T of gamma 0 should be related to T of gamma 1 over the proof that gamma 0 and gamma 1 are related, right? And again, if gamma is trivial, then this is just an element of A, so it's just an element of the setoid as you wanted, but it could be that the context is non-empty, and then we really have to be respecting the quality of the context, right? Okay, and then we can show that this model supports pi types, sigma types, identity types, inductive types, if the meta theory does. Sorry, identity I should put on the next line. So when we constructed the function types, we really used the function types of the meta theory. And when we constructed products, we used the products of the meta theory. Similarly, when we constructed natural numbers, we used the natural numbers of the meta theory, right? So we can carry all of these over. But for things like the identity type, quotient types, and function extensionality, we get this even if the meta theory does not support them.
Why does it not have universes? Oh,
yeah, you can have universes as well. Yeah. It depends a little bit what you mean by a universe. If you mean an open universe or a closed universe.
Okay, but then my question is, does it satisfy universe extensionality?
Yes, I think it does satisfy universe
So
extension.
is it like the Hoffman-Schreiber model?
Yeah, so this is like the baby version of the groupoid model. Yeah. Okay, but the point is you get quotient types and functional extensionality, for example, for free, right?
And uniqueness of identity types.
And uniqueness of identity proofs for free, yes. And if you don't want uniqueness of identity proofs, then you need to grow up and look at more complicated models. Groupoids or infinity groupoids. Or, yeah. Right, I have a little bit of time left. So let me just sketch what's happening with countable choice, because I think that would be good. So the standard way I'm thinking of the axiom of choice, or one of the standard ways, is that if we have for every x in A, there exists B in B. I realize my x and b's are a bit inconsistent, but put this A instead. So if I know that for every A in A there exists a B satisfying some property, then the axiom of choice says that I can find a choice function, so there exists an f from A to B, which is going to pick out this B for every A for me, such that for all A in A are of A, B, right? F. A, F of A, yeah. So there is a function which picks out the B and it still satisfies the specification, right? And the axiom of, okay, what do I mean by exists? Exists x in A P. By this, I mean the propositional truncation of sigma x in A P, which in setoids is the setoid where we have a sigma as the underlying thing. And equality is given by always true, right? So you still have to give the data, but you have to treat everything the same, right? So it really should be a logical exist. And in particular, that means that in order to write the function out of this, you really can't care which particular A you get given, right? Because you're promising that you respect equality and they should all be the same, right? So you could try to prove this in setoids, and you're going to fail. So instead, let's look at the axiom of countable choice. Which is the same, but where A is the type of natural numbers, right? So rather than making A many choices, we're just making countably many choices. And why do people care about countable choice? Well, it's because if you pick A to be anything smaller than this, so a finite number of choices, then it's just provable in set theory or type theory or whatever, basically because you can look at all of the witnesses beforehand, and then you have them all in your hand, and then you can define the function. That doesn't work if it's countable, because then you have to unpack an infinite number of existentials before you define the function, which doesn't work, right? But in setoids, we can actually prove the axiom of countable choice. Okay, why is this? Well, let's assume we are given a proof of this. So a term in context gamma of this type for all A and A exists, B and B are A, B. And we want to produce such a term, right? What is such a term? Well, it's something in the underlying sigma type. And actually, we don't have to worry about preserving equality, but that's not so important. But we do want to construct this function. That's the thing that's hard, right? So given such a term, call it H for hypothesis, then what we can do, we can construct, if we take the underlying term of H, that's going to be a function which takes an A and gives us a pair of these things. So if I compose that with the first projection, then that's going to be a function from A to the underlying type of B, right? So I could, because with setoids we always have these witnesses around, we can always produce this. The thing that's usually a problem is to show that this function really is a set of morphism and respects equality, right? So we need to show that if x0 is related to 1 in A, then first of H of x0 is related to first of H of x1 in B, right? So in general, there's no reason why this should be the case, right? We just have some random operation like this, and we've thrown away all of the equality information here. So it's always trivially going to respect equality, which is why we can't prove the general maximum of choice. But if A now is the natural numbers, then we have that x0 is related to x1 in the type of natural numbers, and that only works if x0 is actually the same as x1, right? Up to our meta notion of equality.
Sorry, we fix the natural number setoid, yes, with the pointwise.
Yes, so I'm assuming that the natural numbers really is the natural numbers with the universal property of the natural numbers, right? Yeah. Okay, but if x0 is literally the same as x1, then our proof obligation here is just that something is related to itself, which we know by reflexivity of B, right? So hence, we do have that this function respects equality in this particular case, but not in the general case. So we see that actually from the point of view of setoids, it's not so much the fact that it's countable, it's the fact that it's discrete in some sense, right? That's what makes it possible.
If the setoid relation is the actual
Yeah. So note, in general, we have axiom of choice from A to B for discrete A. So A with this property, right? In particular, for A being 2 to the n, if the meta theory has Phanext. So 2 to the n, of course, is the prototypical uncountable type, right? But we can actually prove uncountable choice if we have Phanext in the meta theory, because then again, functions this type, things are going to be equal here if and only if they are pointwise equal if you have Phanext in the meta theory, and hence it's discrete, and then we can do the same proof.
But we still can't prove the original one because we don't have and we've thrown away our equality notion. Right?
Yeah.
But so your A was a quotient, and you've done the quotient in raising setoid relation.
Yeah, then it wouldn't work, right? So we could have it for this. We couldn't have it for the real numbers, for example, because the real numbers would have such a quotient. But again, it's not really about the cardinality of the thing. It's more about the complexity of its equality relation. Right?
I mean, it's a kind of very classical example where you have a thing which notionally has 2 points in it, but you can't have some very evil.
Right. So I think you're kind of rediscovering the proof that excluded middle follows from unrestricted choice.
Yeah, I think so. Yeah, I think it's sort of maybe that.
Yeah.
Points of
Just go back to what I said about the value of the unit is a truth value. You could also an endless set of 2 points, one of which is finite time.